So I'd like for you to pick two numbers, a and b, such that a is less than b. Mine are going to be a equals -3 and b is equal to 2, but you can't use mine. Use your own.
Like one is positive or one is negative?
No. I only require that one be smaller than the other. Okay? And draw coordinate axes and put your a and b on the coordinate axes like so. Now what we're going to do is we're going to create a randomly chosen function here, and each one of us is going to have a different randomly chosen function. So to get started, I want you to pick two numbers out of thin air to be f of a and f of b. And the only requirement is that I don't want f of a to be equal to f of b. So pick two randomly chosen numbers to be f of a and f of b that are different from each other. Mine are going to be 1 and the square root of pi. Just because I feel like it. And then, once you've chosen your two randomly chosen numbers here, plot those points. So a, f of a is going to be -3, 1, and b, f of b is going to be 2, square root of pi. And I don't know what the square root of pi is, but it's going to be a little bit less than 2 and a little bigger than 1. Okay? Does everybody have 2 points? Excellent. Now, here's what I want you to do. Take your pencil and draw a continuous function that connects these 2 points. You can go straight across if you wish. My continuous function is going to look like this. The only requirements that I have are that you draw a function, so you can't double back on yourself. And the function has to be continuous, so it has to be all in one pencil stroke. Okay, everybody got their continuous functions drawn? Good. Now, here's our last thing. I want you to choose a number L such that L is between f of a and f of b. Now, my f of b happens to be bigger than my f of a, so I do it like this. But if your f of b is smaller than your f of a, then you would switch these two. Just make L in between those two values. Yes?
I said f of a is 2 and f of b is 3.
That's fine. So choose an L between 2 and 3. There's an infinite number of choices you've got there. You're not out of numbers. Let's see, what should I choose that's definitely between 1 and the square root of pi? Well, that's tough. The square root of 3.1 is going to be smaller than 2. Yeah? 1.1? Yes, 1.1 squared is 1.21, so that should work. So I'm going to choose my L is 1.1. All right? Now that you've chosen your L, do you all have your L's? I'm going to ask you to do something, and I'm going to make a prediction. I want you to draw a horizontal line, y equals L, through the axis right here. And here's my prediction. My prediction is that no matter what curve you have drawn, so long as it's continuous, and no matter what value of L you have picked, so long as it's between f of a and f of b, your horizontal line intersects your curve at least once. Am I right? Raise your hand if I'm right on your curve. 100%, every single time. Yeah, how did I do that? Actually, it's fairly straightforward. I have a theorem. And here's my theorem called the Intermediate Value Theorem. And we aren't going to prove this theorem today. We'll actually prove this theorem in Calc 2. The intermediate value theorem says this. If, and that word if is the signal that our condition is about to start, if f of x is continuous on the closed interval a to b, and L is between f of a and f of b, the reason I had you make f of a and f of b be different numbers was so that we could pick something between them. So if those two conditions are true, then, and that's the signal that we have our conclusion, there is a C somewhere between A and B such that f of C equals L. Now let me explain the language because my other class was a little confused by this. This little E right here is pronounced in or belongs to. And the picture that I have is that I have A and B like this, and I'm going to pick a C that is somewhere in between. So C is an element of or is in or belongs to the interval A to B. And the colon right here is pronounced such that. So the way to read this is, if we meet the two conditions, continuous function and L is between f of a and f of b, then there is a C such that, somewhere between A and B, such that f of c is equal to L. In other words, if I draw the horizontal line, y equals L, it will cut through the curve at least once. And here is at least once for me. This could be my C. This one could also be a C value, and that could also be a C value. So there might be more than one, but there's at least one. And if I have more than one, I could number them, like C1, C2, C3. But the intermediate value theorem guarantees that there is a C. So just to emphasize the conditions and conclusion, conditions, continuous function on the closed interval, and L is anywhere between f of a and f of b, then I can conclude that there will be a C in A and B such that f of c is equal to L. Yes?
So that because L is between f of a and f of b, and f of c is equal to L, so that means C is between A and B.
Yes, I'm guaranteed a C between A and B so that f of c is equal to L. Yep. Okay? Okay. Now, there are some different applications of this, and I have a mathy application and I have a more interesting non-mathy application. I'm going to do the mathy application first, and then if we have time, we'll do the other one. Our math application of the intermediate value theorem is solving for roots by the bisection method. And I'm about to explain how that works. And our setup is this. Suppose I have the polynomial f of x equals x cubed plus x plus 1. And I want to find the root, or the zero, of my polynomial by setting the polynomial equal to 0. Still together. One more time. There we go. All right, so does everybody understand the situation? If I were to look on a graph, my graph looks something like this. What I'm looking for is this guy right here. Now here's the problem. Algebraically, I don't know a formula for solving for cubics. There is actually such a formula, and I never bothered to remember it. It was invented in the 16th century in order to win an math contest. Not kidding. But it basically involves taking this cubic equation and rewriting it so that you have all the difference of cubes. But in any event, it's too complicated to remember. And so what I'd like to do instead is to estimate that root. And I'm going to use the intermediate value theorem to do it. And my setup is this. I look at these coefficients, and they're small, 1, 1, and 1. So I figure that my root is probably small also. Does that seem reasonable? So I'm going to just start guessing. Why not? And I'm going to guess maybe x equals -1. That seems reasonable. So I'm going to try that, and I'm going to call that my first guess on the number x0. And I'm going to evaluate f of x0. What do I get when I evaluate f of x0? -1. That's exactly right. Okay. Well, that's too low. I wanted to get 0, and instead I guessed -1. I got -1 down here. That's too low. So I'm going to try to go in this direction. Maybe I could guess x1 equals 0. And what is f of x1? That's 1. Yep. That's too high. You can see my graph is not really to scale here. That's okay. That's too high. But now I can use the intermediate value theorem to come to a remarkable conclusion. Since, what do you notice about the sign of f of x0? It's negative. But what do you notice about the sign of f of x1? And I'm looking for an x so that f of x is equal to 0. Do you suspect strongly that the x I'm looking for is between x0 and x1? That makes sense. Do I know for a fact that has to be true? Yes, because f is a continuous function. What type of function is it? It's polynomial, because it's polynomial, exactly. So it's a continuous function on the interval -1 to 0, so it meets the first condition of the intermediate value theorem. And 0 is a number that is between f of -1 and f of 0. F of -1 is -1, f of 0 is positive. 0 is in between, which is the second condition for the intermediate value theorem. Therefore, there is a c somewhere between -1 and 0, such that f of c is equal to 0. And that's the conclusion guaranteed by the intermediate value theorem. So I have, with just 2 guessing checks, captured a range of x's that my root has to live in. I've taken the entire real line and I've now narrowed it down to a single small interval from -1 to 0. That's pretty powerful. The c that we're talking about is in fact the root that I'm looking for. Does that make sense? So the intermediate value theorem guarantees that I have a root between -1 and 0. Well, I can do better than that. And the way in which I'm going to do better is by a method called bisection. So watch. Let's take our real line from -1 to 0. Do it in black here. And these are going to be our x values. And I'm now going to keep track of the sign of f of x on different values. So right up here, I'm going to keep subtract the sine of f of x. And so far, what I have found is that f of negative 1 has a negative sign, and f of 0 has a positive sign. Does that make sense to everybody so far? F of negative 1 was negative 1, f of 0 was positive. Okay? Okay. Now, I don't know where my 0 is. It's in here somewhere. So I figured that a reasonable guess could be halfway between the average of x0 and x1. As a first guess. So I'm going to make a second guess that x2 would be the average of x0 and x1. And what is the average of negative 1 and 0? Negative 0.5. So that now gives me a new guess to try, negative 0.5 for my 0. Now, if I wanted to, I could evaluate f of negative 0.5 by hand. I'm a little lazy and a little bit in a hurry, so I'm actually going to do it. And when I take and evaluate negative 0.5 cubed minus 0.5 plus 1, I get 0.375. So that, let's have our results off to the side over here. Not there. Yeah. And f of x0 was negative 1, f of 0 was 1, and according to the calculator, f of negative 0.5 was positive 0.375. Now I want you to notice two things about it. First of all, notice the sign is positive. Second of all, notice that we are closer to 0 than we were before. We're making progress. So when I go back over to my number line right here, I'm going to put a positive sign in for f of 0.375. Now here's the value of doing this. I've cut the range in half, that's right. And I can now eliminate half of my numbers. Which half? No, this is the half I want to keep. This is the half I want to eliminate because my 0 has to be in between here because f of negative 1 is less than 0, f of negative 0.5 is greater than 0, so there is a c between negative 1 and negative 0.5 such that f of c is equal to 0. It's the intermediate value theorem again. Does that make sense so far? Wow. I did it once. I can do it again. I can take the average of negative 1 and negative 0.5. What is that average? That's right, negative 0.75. And I can evaluate f at negative 0.75 pretty easily. And when I do, I get negative 0.1719. You know what? I'm actually going to come back and change the color of mine. So that my colors match the positive and negatives. So here, and when I did negative 0.75, what I got was a negative value. And this allows me to, again, cross off half of my x values and keep only the ones that give opposite sign threat. So that my next guess is now going to be the average of those two. And what would that be?
Negative 6.6.
Okay, and I can plug that in. Negative point. 625 to the third minus 0.625 plus 1, and I get 0.1309. Okay. That's a positive value. So I can go right here, mark my 0.625, give myself a nice positive sign, which lets me cross off that set of x values. And you see what I'm doing. I'm getting closer and closer to my 0. But I'm doing it in a smart way. I'm eliminating fully half of my guesses all at once. Well, we'll try one more. And the average of these two, at this point, kind of like beyond my mental math. So, and so my x that I should try, no, that's wrong. Negative 0.625 minus 0.75 divided by 2. There we go. Is negative 0.6875. And when I try that, oh, that's horrible. I get negative 0.0215. Hey, we're getting better. Notice that I'm getting closer and closer here. I'm also getting closer and closer to 0 here. How many times do you think I would have to go down to get all the way to 0.0001? 3 times as much? So something like 15 tries? That's probably about right. That's a pretty good guess. Yep. Because you're noticing that basically we're improving 1 decimal place about every 3 or 4 tries.
You have to keep doing this until you find the close to here.
You have to keep doing this until you find an answer. Now, this is a horrible way for humans to have to do it because it's so computationally intensive. But it's the best way we can think of right now. So if you're like stuck on a desert island and you've got to do this, find the zero so that you can make a helicopter out of coconut so you can get off the island, then this would be the best way to go about it that you know so far. We would like a better method, and once we have derivatives, we'll be able to actually do a better method that gets us really close in about 2 or 3 iterations for this function. Okay? But our better method will have a downside, and that is sometimes it fails. This method cannot fail. It cannot fail. It just requires a lot of patience. Here's another thing. If I have a computer to do these calculations for me, done. Right? So that this is actually not a horrible way to go. But usually, computer scientists will use it as a backup method if the other method I mentioned fails. Okay. So, this is the bisection method, and just to recap, especially if you're watching bisection method, first we find an x0 and an x1. Our problem is to solve f of x equals 0. Find x0 and x1 so that f of x0 and f of x1 have opposite signs. And as soon as I have done that, then the intermediate value theorem guarantees that there must be a 0 in between, as long as my f is a continuous function. And that's a pretty modest claim. I just can't have any jumps, that's all. Okay? Then, I'm going to repeat the following process. Choose the average of the previous 2 x's. And evaluate. Choose the x's so that f of x is up to its sums. And that's what we did with our number line right here. This number line is a great way to keep track of things here. We kept on choosing x's so that we had a plus sign and we had a minus sign right here. So we're trapping our 0 in between the two values. And we just repeat that until we get as close to 0 as we need to get. If I need a 0 to 2 places, then I can pretty much stop right here. Maybe I'd go one more try. If I need a 0 to 4 places, then I'd have to go all the way down there. Does that make sense?
Yeah.
Yeah.
So what is that?
Well, we need to know some things about slopes of tangent before I can explain another one. But this is our bisection method, and it's slow, but reliable. Very, very reliable.
Do you have like a word depression?
Yeah. And I don't kill you.
I keep this kind of question on the class.
If I do, it will not be a very time-consuming question. Because I can't, right? I mean, you've only got 50 minutes. And so I'm not going to give you a question that asks you to walk through lots of times. I can imagine myself asking you to do this maybe once.
The homework. It's only one question.
Right. But then there's some other questions about the intermediate value theorem. Now, we're out of time, so I didn't get to do my other application list. I might do it as part of our review tomorrow. Tomorrow we're going to review, right? So come ready knowing your definition of terms. That's the basis of everything that we do. I'll see you tomorrow.